Assume that matrix A is row equivalent to matrix B, and find bases for the null space of A and the column space of A. So part A, we want to find a basis for the null space of matrix A. So to make this a little easier for ourselves, let's start by noting that since matrix A is row equivalent to matrix B, and matrix B is in echelon form, let's row reduce the augmented matrix B with the 0 vector. So we have matrix B, which is 1, 0, 0, 0, 2, 0, 0, 0, 0, 2, 0, 0, 2, minus 2, 0, 0. And last but not least, we have 7, 2, negative 6, 0. Again, we're augmenting this with our 0 vector. So looking at this augmented matrix, we can see that our first pivot position is all set. Moving on to our second pivot here. And actually, we can simply reduce this to get us started. So let's do 1/2 row 2, and then we'll do negative 1/6 times the third row, which leaves us with the equivalent matrix 1, 2, 0, 2, 7. We have 0, 0, 1, minus 1, 1. Then we have 0, 0, 0, 0, 1, and 0, 0, 0, 0, 0. Phew. All right, so we now have our first pivot is good, our second pivot is good. So moving on to our third and final pivot, we want to use this to eliminate the entries above it. So we'll need to do this in 2 steps. We'll do minus 7 times the third row plus the first row to attain the new first row. And we'll also do minus the third row plus the second row to establish the new second row. And so this leaves us with the equivalent augmented matrix. So our first row is going to be 1, 2, 0, 2, 0. We then have 0, 0, 1, negative 1, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0. And so we have attained that row-reduced echelon form. And this is going to be equivalent to the linear system. X sub 1 is equal to minus 2 times x sub 2 minus 2 times x sub 4. We have that x sub 2 is free. We then can see that we have x sub 3 is equal to positive x sub 4. We need more room already. We also have that x sub 4 is free. And then last but not least, we have that x sub 5 is equal to 0. So we now want to convert this to the parametric vector form of our general solution. So we have this vector x in R5 defined by x sub 1, x sub 2, x sub 3, x sub 4, x sub 5. And plugging in what we just found, we've established the linear system here. We have minus 2 times x sub 2 minus 2 times x sub 4. We have that x sub 2 is free. We have that x sub 3 is equal to x sub 4. We have that x sub 4 is free. And then we have x sub 5 is 0. So we can just put a happy little 0 there. So that's going to go into both columns. So it may be more beneficial to write it as 0, 0. And then again, to separate this out so we can see the basis, we want to incorporate zeros into all those missing entries. And so our beautiful final answer is vector x is defined by x sub 2 multiplied by the column vector -2, 1, 0, 0, 0 plus x sub 4 multiplied by the column vector -2, 0, 1, 1, 0. And this is such that x sub 2 and x sub 4 are free. And so this is the general solution to our matrix. And we use this to find the column space, or excuse me, the null space of matrix A. So we can say that therefore vector x is a linear combination of the vectors so it's defined by the linear combination of the vectors -2, 1, 0, 0, 0 and the vector -2, 0, 1, 1, 0. And this is the basis for the null space of A. Woohoo! So part A is all set, and we're ready now to go ahead and find a basis for the column space of A. So we're now ready to look at part B, where we're asked to find a basis for the column space of A. So we want to begin by recalling that the pivot columns of an m by n matrix A form the basis for the column space of A. So what this is informing us is that since matrix A is row equivalent to matrix B, they have the same pivots, or the same pivot columns. So we already know from part A that we have pivot columns in vector B sub 1, in vector B sub 3, and vector B sub 5. So this means that the pivots of matrix A so the pivot columns of matrix A are going to be vector A sub 1, vector A sub 3, and vector A sub 5. So you just want to be mindful here that we have to use the pivot columns of A. So we're using A sub 1, A sub 3, and A sub 5. So we can write our beautiful final answer, a basis for the column space of matrix A is defined by the set of vectors 1, 1, 4, 2, 2, 0, -4, 0, and last but not least, 6, 6, 5, 5. And so this is our beautiful final answer to part B.